Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. And a very good day to everyone. And for today, for this session, I will just continue the lecture on the next topic in the Townsend principle, and we will look in extra detail on the numerical approach. Okay. In general, by now we understand that in Townsend principle, Townsend have described four main regions, in which region 1, 2, 3 and 4. If I can quickly recap on this region 1 in this year, if you can see, it is what we call as a photoionization process. I don't want to explain it detail as I explained it earlier. And then the next region will be region 2. In this region, we call it as saturated photoionization process, in which further increment of the voltage will not cause an increment in the current, so we call it saturated. And then in region 3, we know it is a it is about the ionization by collisions. Okay, in this region 3, in which the photoionization occurred by collision process, and that's why we can see the increment of current, and finally in region 4, this is what we known as the sustainable ionization process, in which or in other words, we call it as a total breakdown or total failure of the gas insulation material, in which the ionization process, as I explained before, it is a process of discharge or the breakdown of the gas. And if it is sustainable, means that it doesn't require any independent source of to initiate or to trigger for the further breakdown. So means that the ionization process in this region actually is independent of any external source. For example, if we take out the source of UV light, the process or the breakdown will occur, and the current will increase independently. We cannot control the amount of current. Okay. This is closely related to what we're going to look in the numerical approach about the alpha and gamma, or we call it as a primary and secondary coefficient in Townsend principle. Okay, we're not going to learn in great detail about how this formula is derived. We're not interested in that. But in this case, it is expected for a student to really understand the formula and how to use it. Okay, how to use it. Okay, if we relate to region 4, in which we call it as the independent or sustainable ionization process, or total breakdown. If you can see, the Townsend coefficient condition satisfy the breakdown sustained in region 4. Okay, the self-sustained breakdown in region 4. Okay, this involves this formula. We can classify as and okay, if you look in detail in this topic, for this section, the gamma is referred to the electron emitted from cathode. Okay, the numbers of electron emitted from cathode bombarded by the positive ion, and the N plus is actually the electron release from the cathode, okay, per second, right? There is a difference between the gamma coefficients. This is just a number, and while N plus is referring to the electron release per second, okay, per second. Okay, and we can establish a relationship in which n is the numbers of electron reaching the anode per second. Okay, electron reaching the anode. Okay, electron reaching the anode per second. Okay, the total number of electron reaching anode, ataupun in other words is electron reaching the anode electrode per second under steady state condition is given by n is equivalent to n naught, okay, electron, and we have to the power of alpha times d distant gaps over 1 minus gamma, okay, times electron to the power of alpha gaps times gap minus 1. Okay, this is the formula is given by 1.3. Okay, in the steady state current, okay, in the steady state conditions, current is equal to epsilon times n, in which n is equal to this equation 1.3. Equation 1.3, okay, is equivalent to epsilon n naught electron times alpha d divided by 1 minus gamma electron to the power of alpha d minus 1. Okay, this is the equation and we rewrite it as a 1.4. Okay, if we look carefully, alpha and gamma in both scenario in the Thomson principle depend on electric field stress, electric field strength given by E, volt per centimeter, kilovolt per meter. Is depend, means that alpha and gamma is depending on the applied voltage, external applied voltage from the circuit. And if we go in extra detail, if the denominator, okay, the denominator is this one, it becomes 0, the current will become independent, independent of the number of n naught. Okay, therefore, we can say that the Thomson criterion for the breakdown gas, okay, for the breakdown gas is given by, okay, gamma, okay, or secondary coefficients time electron alpha d minus 1 is equal to 1. This is the Thomson, known as the Thomson criterion. Okay, this is known as the Thomson criterion. And if the ED is very large, and the equation can be rewrite as electron alpha d is equivalent to 1 over gamma. This is just a brief on the derivations. Okay, okay, if you look if you look for a voltage above V3 and less than V4, okay, this is known as region 3, right? Region 3, and the process is not satisfied enough to cause a breakdown in gas. That's why in okay, and this is when I is less than, okay, if you can look carefully here, is less than, in which for region 4 is equal to 1, right? Okay, at voltage 4 and beyond, the breakdown occurred conditions. The breakdown occurred and consider satisfy the criteria 1 is equal to this is actually gamma. This is actually gamma. Electron AD minus 1. Okay, this is gamma. Okay, and okay, at V4, V at the voltage 4, voltage at the initiation of the region 4. This is what is termed by breakdown voltage, VB. Okay, that is where the breakdown in the gas occurred, and we classify as a VB. That is how the Townsend described how the initiation of the failure in the gas dielectric material from the physics theory, the bombardment of the positive and negative ion, which trigger for the current flow, and the failure of which lead to the breakdown of the gas, the dielectric material. Okay, and we classify as EB. Okay, for voltage more than V, okay, the current circuit, we have to be aware that the current within the circuit can only be determined by the external resistance, because we cannot control the current within these regions, and the only way to control it is just by the external resistance. And we can actually measure the current in this scenario by using the external resistance, and this is normally referred to kind of the short circuit conditions. It's a total breakdown, like we are, instead of the dielectric in which it should resist the current flow, when the breakdown happen, it'll become conductive and it'll become short circuit, and the current will just flow indefinitely. And the only way to control the current flow is just by adding the external resistor. Once we have the resistor within this breakdown region, then only we can control. Without the external resistor, we definitely cannot control the current flow. Okay, obviously we look into this one and rearrange equation 1.5, the Townsend breakdown criterion, between an average ionization collision made by 1 electron per second, that can be expressed as, okay, AD, alpha times distance, the gap, is equal to ln times 1 over gamma, 1 over gamma plus 1. Okay, this equation is the condition of the breakdown in the gas. This formula, equation stated as 1.7 here, the one that we will use in many numerical calculation later. Alright, so we don't need to worry about the derivation, but what most important here is just we know how to use and utilize the formula. Okay, plasma, you can some extra knowledge you can read by yourself. You can Google or YouTube for more information about plasma. But in short, it is about when the breakdown occurred. When the breakdown occurred within the within the gases dielectric material, and in which we found the conduction of current that produce some sort of some process that emit light. Okay, the process emit light, this kind of colors, that is what we call as plasma. Interesting color, or spectrum to be precise. Okay, for normal breakdown, it's just a simple arc, which is, we can see orange color. And for the plasma scenario, it happened when it happened when a huge number of electron and proton that cause the breakdown, and it start to produce the spectrum color like this one. That is what we call as plasma. Alright, so we come to this example of tutorial to further understand about the Townsend principle. Okay, for example, okay, estimate the static breakdown voltage. Okay, static breakdown voltage VB. This is the keyword, static breakdown. Why is static breakdown? Because in the Townsend principle, they assume the electric field within the material within the chamber is static, electrostatic conditions of an air gap. Okay, this is also the keyword, air gap. It could be air is a gas, it could be neon, it could be hydrogen, it could be CO2, any gas that we use as an insulator at the pressure of, okay, 100 mmHg pressure. Okay, between two parallel plate. This is also the keyword for you to understand. When it mentioned it is a parallel plate, that means we know it is a Townsend in uniform electric field. Okay, here is given alpha, the ratio of alpha to the pressure is given by this figure. Sorry. Okay, alpha. Okay, the ratio of alpha and pressure is given by this pressure, by this illustration, by this plot against EP, electric field over pressure. So we have the alpha, primary coefficient, Townsend coefficient, primary Townsend coefficients against the electric field. Both are at a ratio of pressure. Okay, assume gamma. Okay, gamma, the secondary Townsend coefficient as the electron 10 to the power of minus 3 electron per incident positive ion. The gap distance D is 1 centimeter. Estimate the static breakdown voltage for nitrogen, hydrogen, argon, and neon gases as well. Neglect the recombination and attachment. Okay, this is the assumption. This is the assumption in the Townsend in this calculation, in which we try to neglect the successive collisions or successive interaction between the avalanche, or what we call it, the breakdown phenomena. So we need to neglect the recombination effect. Okay, because obviously proton and neutron, proton and electron can be recombined at one stage, and we try to neglect in this for the sake of the calculations. Okay, again, as I mentioned earlier, we just use the formula as given in equation 1.7, in which we know that the alpha distance, okay, alpha D is equivalent to ln times 1 over gamma plus 1. Okay, this. And then we look at this figure. The illustration is figure because the question asked based on this illustration. We understand this one is the plot of the for neon, argon, hydrogen, air, and nitrogen. We have several gases here, and we have the plot. The one is this plot is plot in the logarithmic plot, plot, and the coefficient of field intensified ionization by electron. We call it as a coefficient for electric field ionization by electron. Okay, how to proceed with the calculations? Okay, we understand that the PD, P is the pressure and D is distance, multiply is equal to gap pressure. The pressure within the gap, and the gap is given before is 3 centimeter. 1 or 3. Okay, 1 centimeter. Okay, this is the gap pressure. Distance is equivalent to 100 mm Hg per centimeter. So, because it is mentioned before is 1 centimeter. Okay, at this PD value, gap pressure. Okay, gap pressure. Townsend principle hold good. The Townsend criterion. Okay, we just use the formula. Okay, so AD is equivalent to ln 1 plus 1 over gamma. Gamma is given, okay, gamma is given 10 to the minus of 3. So we will have the AD is equivalent to 6.9 ion pairs. Okay, ion pairs. Ion pairs. The unit is will become ion pairs. Okay, and further calculate, and we know the distance is 1 centimeter. So per centimeter, so this one will become 6.9 per centimeter. That's why we have the 6.9 ion pairs per centimeter. If it is the gap distance is 2 centimeter, then we'll divide it by this one. It'll become like 3 point, more or less 4. We just simplify 3.4 pairs per centimeter. It will not longer 6.9. This is just by because the distance is 1 centimeter, so it's become this one. So when we further calculate, if we divide that by ion pairs, okay, ion pairs over a pressure, okay, because we know the pressure is 100 mmHg is given in the equations here. Air gap, okay, air gap at, okay, pressure gap pressure. The gap pressure is 100 millimeter Hg. Is given, and then we divided both, okay, on the left side and the right side by the pressure. It will give us alpha over pressure is equivalent to 6.9 per ion pairs per centimeter divided by 100. It will then give us a value of 0.069. Okay, and we will get 0.069 ion pairs per centimeter mmHg. So we got this one. This is why we want to calculate this one. We want to calculate alpha over pressure. The only reason to obtain this value is purely because of this plot. Okay, because the plot given, the data or the plot is given to us is actually alpha over pressure. That is why we try to rearrange this formula to obtain the alpha over pressure, so that we can actually locate where is at which point that is 0.069. Okay, in this case 0.6069. Okay, let's work together. This is 0.01, 0.02, 3, 4, 5, and 6. 69. So 0.069, almost 7. So since we are considering for the air, so the value, the cross-section value will be around here, right? The value will be around here. And if we check carefully here, it will give us a value of around 40, 50, 60. So somewhere in here about 59, 58, 57, something around that values. And then if we look here, okay, refer to the graph for air. Okay, EB at this point, they intercept at 54 volt per centimeter. 54 as we calculate before. 54, 40, 50 is somewhere here, as I mentioned to you before. The electric field over the ratio of electric field over the pressure is this value. So we know the value for this one is actually 54. Then from here we should be able to calculate, okay, to calculate the breakdown voltage. In this case, for example, EB is equivalent to 54 times pressure, and we know the pressure is 100 mm per Hg. So we calculate, we obtain 5400 volt per centimeter, which is equivalent to 5.4 kilovolt per centimeter. Okay, we've got these values, and we know that electric field, okay, electric field is can be obtained by voltage divided by the distance, the gaps. Okay, in this case, the voltage, the breakdown voltage can be calculated by rearrange the formula EB, electric field time distance, and distance from which that can be obtained from the equations is 1 centimeter. So eventually we should be able to calculate the static breakdown voltage, which is 5.4 kilovolt. Okay, so we calculate from the data given in this plot. Why we try to calculate this one? Alpha, a primary Townsend coefficient over the pressure, is purely because of the data given here is this one, and the data given here is this one. We try to find the plot, and we try to make an equation from this one, then should allow us to calculate the breakdown voltage. Okay, how about for other gas? Okay, this is for hydrogen, nitrogen, hydrogen, argon, and neon. How about for this gas? In the similar way to this one, okay, we calculate exactly the same, except at this point we need to locate which particular gas that we are looking for. Say if it is neon, so we need to look at the neon, and then in this case alpha over pressure is actually 0.1, and that gives us this value is around 20, I would say 25. Okay, is 15. Okay, 15, 20, 25, 30, 40, and so on. So is the logarithmic scale, so you have to be very careful to locate these values. Okay, 10, 20, 30, 40, 60, and so on. And how about for other gas? If it is air, we need to check for the air. If it is nitrogen, we need to check for the curve of nitrogen. If it is hydrogen, we need to check for hydrogen, right? So the calculation approach is exactly like this one, except for the value, the interception value at this part. So that will give us this formula. So you may try to calculate by yourself and try to cross check these values, whether you get the same value or not. Okay, these are the checkpoint. I don't want to describe this further because it's just the same. And then next, example 2. Again, the same formula, static breakdown. So we know is VB of air gap at, previously we calculate at 100, and now we calculate at 75 pressure and gap pressure. 75, two parallel plate, uniform field, they are the same. The alpha over pressure, the same. Electric field over pressure is again the same. And assume again gamma here is 10 to the minus of 3. Again the same. The gap distance previously is 1 and now is 3.5, so we have to be careful of this. Again, they are exactly the same. So it just play around with some new values, which is the gap pressure. In this case, it is 75, and the gap is actually 3.5. And how we have this formula, and you may calculate by yourself by using the same technique that I explained before. So I don't want to discuss or spend more time on this. So it is exactly the same. We have the solutions, so you can check by yourself. And also for other gases. And also if you look carefully at this formula, the equation is pretty much similar to what we discussed earlier. So I don't want to repeat this. And again, this one, they are just about the same, except in this case gamma. Assume gamma is about 10 to the minus of 5. And the gap distance is 16 millimeter. So be careful with the unit. If be careful with the unit, millimeter or centimeter, you have to be very careful of the unit. Okay, come to the next section. It's about time lag for breakdown. Time lag for breakdown. In short, the breakdown of the gas will not happen at instant. It will not happen at instant means that it would always require a certain period of time before the breakdown occurred. In this case, okay, we classify as the TB, total time for breakdown, is equivalent to TS plus TF. Okay, TS is the statistical okay, this is the statistical time lag, the time lagging, okay, and TF is actually the formative time lag. Okay, what does it mean? Okay, statistical is based on the electron movement, the average electron movement, and then the formative is formative time lag is actually the how this avalanche to form to form or to initiate, to trigger, or to trigger until the trigger of the breakdown. So total breakdown is the is counted from the time from the ionization occurred until it's become total breakdown. Okay, problem with the Townsend principle. Okay, what is the issue with the Townsend principle? Okay, okay, the Townsend suggests that the time lag could happen around 0. Let's just check. Occurred in order of 10 to the minus of 5. Okay, means it is about what? It is about 0. It is about 1. Sorry, it is about less than 1 microsecond, right? It is less than microsecond. Okay, however, okay, the total breakdown, okay, the experiment from other researchers found that the breakdown occurred at further short time, okay, very short time, in order of 10 to the minus of 8. In this case, it means it's about instead of micro, 10 micro, and other experimental work suggests it is nano. Okay, so what we can conclude from here, actually, the Townsend phenomena or Townsend experimental work cannot suggest or cannot describe for a phenomena under a short duration of time, or in other words, transient, or in high voltage term we call it as the impulse. Okay, the impulse is actually the breakdown that occurred in very short period of time, normally in nanoscale and above. That's why we assume that the Townsend principle cannot be used to describe the transient phenomena or the impulse phenomena. Alright, it's not really the issue, but that is the constraint of the for the Townsend experiment. Okay, again, and around this group of researchers proposed another theory, which is a tremor, that I will further explain later. Okay, let's just check this one.